So, this is the last class. There's an exam on the 16th at noon. I'm going to have a practice final out this weekend, then we'll post a solution to it later in the week. The topics covered are what is on the Schedules tab. You can bring a sheet of paper in. It covers, between the final exam and the midterm, we essentially cover the course evenly, so there's some parts from the first half of the course. We'll have a review session. We'll post it on Piazza, or maybe we'll do a doodle poll or something to find out a time that people want it. But the practice final will actually tell you a whole lot of things about the exam. All right. Does anyone have any questions about anything? Yes?
On the Connect website for clickers,
Yes?
some of them are like out of 100.
Oh, I've no idea what the clicker marks are doing. They're all going to be averaged in and done what we said. They're going to be proportional. They're going to divide by the numbers per day, and then you're going to collect the best 2/3 of them and everything else. It took me 2 hours to upload them to Connect, and when I tried to look at them, it's so slow I can't look at them. So I'm going to download them and do what I promised. I just wanted to make sure you had them. I have no idea what it's doing. It's as more opaque to me than it is to you. But we'll do something that's fair. Yes? Sorry, I can't hear. So what happens in the exam is I think it's 30% of the marks are for the final, for the midterm, and 50% of the marks are for the final, right? And this covers the whole course. So if you divide this in half, you'll find that in the first half of the course, so if you think of this as 80%, there's 40 in the first half of the term and 40 in the second half of the term. 40 marks out of this will be for the first half, and 10 marks out of this will be for the first half of the marks. Right, so it'll essentially cover this, right? So approximately 20% of the final mark will be in the first half of the term because the other 30% of the marks were covered in the first midterm. So it's cumulative in that sense, but between them they cover the whole course reasonably evenly. Does that make sense? That seems the only fair way to do it, the only sensible way to do it. So mostly on the second half, but expect some on the first half. Any other questions? All right. So what we've done so far is we've done a whole lot of representations that we've done as we've looked at the dynamics are either being deterministic or stochastic. So we first of all looked at search and CSPs and some stochastic local search and some logic and some planning. And then we looked at belief networks, decision networks, and what we'll call Markov models now. Then we looked at the fully observable cases. We assumed we knew everything. And then we looked at the partially observable cases where we didn't observe what the world was like. Now, in terms of representations, you can view in terms of states or in terms of features. When we did search, we looked in terms of states. And then we were looking in terms of features. When we look at Markov models now, we're going to look in terms of states again, but we're going to talk about not just a finite set. Like when we did decision networks, we looked at just a finite stage. We looked at just a few decisions, like 2 or 3 decisions in a row. But now we're going to look at sort of Markov models. We're going to look at infinitely many decisions. When we looked at preferences, we sort of looked at goals and utilities. And then we looked at sort of rationality and all the things we said were effectively perfect rationality. We could actually compute the effect of everything, except when we did this stochastic local search. Then we looked at this bounded rationality because we could just try and get try to approximate things. So we tried to just get as good a solution as we can. Okay. So what we're going to do today is we're going to talk about Markov models, but it's all really stuff that you've seen before. Does anyone have any questions about this? Okay. So let's, because we always do this, let's start with the clicker questions. Because I know you'd be disappointed with no clicker questions. And this is the clicker question about the simple belief network, S0, S1. I want to know which of the following is not true. All right, does anyone need more time? Does anyone need more time? Yes. C is not true. They're not independent of each other given no evidence. Right, so if you observe S1, it's going to 0, it's going to tell you something about S1, it's going to tell you something about S2 and S3. But if you know the numbers and the values in between, they're independent of each other. Okay, so this is essentially the independence assumption in this structure says that when you know the states in between, that the beforehand and after are independent of each other if you knew sort of the current state is one way to think about it. Okay, any questions about that? So the next question is, we're querying, we want the probability of S2. And we want to know what variables can be pruned before doing inference. All right, how's it going? People need more time? People still need more time? Okay, 3, 2, 1, we'll stop. Right. So S3 and S4 can be pruned. In fact, what we're going to do, this is interesting because what we're doing here is we want to think about these that essentially go on infinitely in the future. Right, we want to think about these models that sort of go S4, S5, and it turns out we can, if we don't observe any of them, we can prune them. They're sort of, the future is irrelevant to us when we're doing the probability of one of these states. So if you think about this as an infinite sequence of things, all the future, according to the Bayes net model, is irrelevant to us. So if we're thinking about S2, we only need to think about the past. We don't need to think about the future. Right, sort of, if we don't observe anything about the future, we can sum it all out and we get no information. So I don't need to tell you that for this network because you already know it from the previous definition. So are there any questions about this? So we can prune off the future when we're just reasoning with these models. And so here's another model. And I want to know what probabilities need to be specified to this model. All right, how are we going? Does anyone need more time? So we'll still need more time. Okay, 3, 2, 1, we'll stop. Oh. That's interesting. There's enough people. A is the right answer. We need every variable given its parents. It's the same definition we've seen all the time. Every variable given its parents. That's what we need in all of these things. So in fact, what's interesting about C is that we don't need this. Right? In some sense, we don't need the observations given the previous states. We only need the observations given the current state. The previous states are independent of the observation. So if you know the current state, that's the only thing you need to know to work out what the observation is. The observations here only depend on the current state. They don't depend on your history of states in here. So A is the right answer. Any questions about that? I'm a bit worried people are getting this wrong because it's something you've got to, I'm just going to assume you know and you're just going to do it. So you really need to know it for the, if you don't know it for the exam, you'll be in trouble, okay? Any questions? So it's each variable given its parents. That's what we need in here. Okay. Okay. Any other questions about that? All right. So what we're going to do today is we're going to just play with these models. We're just going to give a few examples of these models. We'll tell you how a simple Markov chain made a few people a few $billion. A hidden Markov model will show how localization works. For example, a Google car works. And then we'll tell you how just by predictive models of natural language. They're all essentially the same for how these work. So here's a Markov chain. We did this as one we did last time. We just did this. We know to specify the dynamics. The independence is is the probability of the SI given the previous history only depends on the previous value. In some sense, this is the definition of state. Is the state is all the information about how the world works so that the future is independent of the past, is a way of thinking about this. Okay, the future is one of the ways of thinking about this is the future is independent of the past given the present. Okay, are there any questions about this? So this is sort of a simple model. All right. What we're going to do is do something called a stationary Markov chain. Is really, it says the transition probabilities are going to be don't depend on the time. So how the world works doesn't depend on the time. It works the same at time 5 as it does at time 500. So the probability of S of I plus 1 given S of I is the same for different i's. So the world works the same now as it does at other times. And the reason we're going to do that is now we only need to do two things. We now need to only specify the initial state and how the dynamics of the world, how the world works, how the probability of some state works given the previous state. So this is the simple model. It's often the natural model. And now we can extend this infinitely because we just keep adding on times because we don't know the dynamics. Okay, so we keep knowing how this is going to work. Okay, so stationary just means it's time invariant. It doesn't depend on the time. Okay, any questions? Is that clear? Clear because we're going to keep using this stationary. All right, so here's sort of an interesting model. So here's a model of web pages, and it's going to be the state of SI is the set of all web pages. So we have all of the web pages in the world, and we're going to start, initially we have a uniform distribution over the web pages. And now we're going to specify this dynamics for the probability of, so big N is the number of web pages, so it's a uniform distribution initially. So it's just the same one we had before. So we have S0. And now we have S1 given S0. Right, so we need to specify this. And what we're going to do is we want to specify, this is all the web pages. So now we want to specify the probability of going from web page PK to web page PJ, which is the probability of you're in PJ. So you're in PK, you're in page PK. So page PK, right, has all these links to it. It's just a web page with links that point to otherwise. Right, they point to other web pages. And now what's going to happen is that there's going to be some D that you keep surfing. So you're either going to stop surfing is the first case. There's 1 minus D, you're going to stop surfing, in which case you get a uniform distribution over the web pages. And with probability D, you're going to keep going. And the probability D you keep going says, just with random chance, you're going to pick one of these three at random, and you're going to move to this web page. Or with random chance, you're going to move to this web page. So with 1 on 3, you're going to move to one of these web pages. But if you don't have any web pages, you're going to pick one at random. Does that make sense? That's the dynamics. So you're just going to random surfing model. Right? Does that make sense? If you're at this web page, you're going to, with probability 0.85, you're going to move to one of these. With probability 15, you're just going to pick a random web page. Okay, does that make sense? So we just have this very random web page. So it's simple. You know how to implement this. Right? You know how to implement this. You have a random web page. We're going to do a forward simulation. We're going to sum out that and we get a new one. We're going to sum out this and we get a new one. Okay? You know how to implement this. You know because this, what we're doing here. So this model here is called, this Markov chain, if you keep going long enough, it converges to a distribution over web pages. And this was the very first what Brin and Page published as PageRank, and they started a company called Google you might have heard of, which is based on this. You know how they implemented it. They started here and they kept doing variable elimination along to the end. They got to, I think they went for 50 stages with 322 million links, and they ended up with a ranking of web pages, because what happens is that the most popular web pages keep being revisited. Right? And it's hard to trick this web page. If you're pointed to by a popular web page, you become popular. It's hard to do it. And so you know how it's implemented. It's just you start off with this, you keep summing out these variables, and then for all the web pages until you do it. Okay? So now you know Markov chains, you know how Google what they started with Google with. Okay? So it's just what we've seen before. Okay, so this is how PageRank works. Are there any questions about this? Okay, so it's nice models, these Bayes nets with these Markov chains. We can tell you how lots of things work. All right, next one. So this is called a hidden Markov model. This is this belief network. So it's this, we have the same states as before, but now we have an observation model. Now we have, given the state, we're going to talk about what the observation model is here. So we have this. Okay, so we're going to keep going on forever. You have a model here. The observations depend only on the state. And so as we saw before, the probability that you need to specify the initial conditions here. You need to specify the dynamics, how the world works. And you need to specify the sensor model, how the model here depends on this. Okay, so let's. All right, so here's this model. Now we also know how to implement it. So let's suppose, what we're going to do is we want to find out the probability of some particular state given our observation history. Right, so that's the problem we're going to do. It's called filtering. But we know how to do that. If I is 0, we can prune off the future. We did that. We can prune off the future. We just have this simple Bayes net model. We sum out this variable and multiply it by this. Right? Once we've got the probability distribution on this and we observe this variable and we want to query this one, well, we know how to do that. We sum out this variable, we maximize over this, and we condition on this variable, build up that factor, and we do this. This is what you did in the last assignment. Okay? If you want to now query this variable, we have the distribution on this variable. We observe this one, we multiply it by this, and sum out this variable. And we keep going. Right? The same we've done before. Okay, so if we want to do this, all we're going to do is just variable elimination. We keep observing this, we sum out this. Right, then we have this given this, we're going to sum out this variable, we're going to multiply it by this factor. Okay? It's just what we've done before. It's the same thing you did in the last assignment. All right, is there any questions about that? We'll give an example in a second. So what we're going to do is we're going to slightly augment it. We're going to have we're going to have actions in there as well, but actions are just other variables, and the location here, the actions affect the location. So now this is the state is now the location. We now know the actions that we carry out, and now we're going to keep, now we're going to update the location given the observations about the world. So imagine this is Google car. The observation, it has Google Maps, it knows where it is, it has this Google Street View. This observation here is Google Street View. And if you just use Google Street View to find out where you are, you're going to get lost, you're going to not know where you are. You see a picture of houses, you have no idea where it is. But imagine you knew your location from a second ago. And now you're going to predict where you're going to be. And if you keep predicting where you're going to be, you're going to get lots of errors. If you don't observe the world, you're going to get lots of errors. But now what this tells us, we're going to predict where we're going to be, but now we're going to update it based on our observations. So we're going to predict where we were a second ago. We're going to update, we're going to observe the world. We're going to update where we are. We're going to predict where we were before. We're going to observe the world. We're going to predict where we are, and we're going to observe the world. Right? That's how. And if you tried to do either of them by themselves, you'd end up in trouble. If you tried to just do vision and look at Street View and find out where you were, you're in trouble. That's too complicated to do, so let's do a simpler example. So here's a simpler example. Okay, here's a simpler example, but it's the same way that the Street View. This is actually this is an example due to Sebastian Thrun, who was the guy that Google hired to do the Google car. So this is his example. So what we have is this circular corridor with 16 locations, and it's drawn here. There are doors at these positions 2, 4, 6, 8, 10, 12, 14. We have noisy sensors, very noisy sensors. So there are noisy sensors of doors. That's all you can see is whether there's a door or not. With the dynamics are stochastic, the robot starts at an unknown location, has to find itself. Right? If you think about this, so here's the dynamics. So here's the model. If you're at a door, you're going to observe a door with probability 0.8. So there's 20% error in observing doors. Right? There's a 10%, so if you're not at a door and you observe a door, then if you're not at a door, you're going to observe not a door with probability 0.9. So with probability 0.1, if you're not at a door, you're going to observe a door. So there's a 10% error of those, of not at a door. So it's sort of pretty noisy. It's a pretty noisy sensing model. And here's my dynamics model that says if I'm at a position so I have two reactions. I can go right or left. And if I have an action, I go right, then with probability 0.1, I stay at the same location. That's what that says. The first one says if the location at time t was to go right and my location was L, then my location at time t plus 1 is also L with probability 0.1. With probability 0.8, I'm going to end up going where I predict it is. So it's only has 80% reliability in getting where it's going to do. It has, with probability 0.02, so there's a 0.2% chance of going to a random location, to any other location, and the rest of it is about 0.01, less than that, of going to 2 steps right, so you can overshoot. So that's the dynamics. And all of this goes in a cycle, so we can do this. And actually, the left goes the same way. Okay, so let's look at. So here's an example of this. So we wrote a little applet to do this, and I'll find it here. And so here, what was happening here is that these are exactly the same positions, 0 to 15 as in here. So it's these same locations. We're going to start at position 4. We're assuming the robot that starts at position 4, and this measures our belief state. So this is the probability distribution over the states according to the agent. So now we have, assuming it knows where it is, and if you move right, then you end up, so the bottom right is the previous, and the top one is the current. So if we move right, then with 0.8, we move right. With 0.01, we're going to stay the same. With probability 0.074, we're going to move 2 steps to the right, and everyone else has this thing, right? That was the dynamics I said before. Okay, so with 2 steps to the right, it's just exactly the same algorithm we saw before. We end up with, right, each one of these has a probability of moving where it's going. And so now we have And so now, the bulk of it sort of moves one step to the right, but it's only 65% of them are move 2 steps to the right. And if I move 3 steps, then it gets more uneven. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And at 16 steps, we sort of know it's there, right? So you can get, so it's only a 16% chance, and there's a 16% chance that you're there, but you're pretty unlikely to be way over at 15, right? You sort of, once you've done this, you're very unlikely to have done it. So you get lost pretty quickly here, right? There's only a sort of 1 in 6 chance that you're at any of these things. Okay, so I understand that's the dynamics. Right, but then we're going to make observations. So let's show what you can do here. So it's a noisy, very noisy system. And it's a very so you have noisy dynamics, you have noisy observations, and there's not much information in here. Right? There's only doors and not doors. So let's pretend we're doing something. Let's reset this. So we're going to pretend we're at something. So let's pretend we start somewhere. Give me a number towards where we start. We're going to start at 8. Okay, we're going to start here. We're going to see if we can find ourselves. Okay, so we're going to observe. We're at position 8. What are we going to observe? Let's observe no door. Let's not be so noisy now. Let's observe no door. If we observe no door, we multiply it all by. So the previous one was the uniform distribution. We had no idea where we were. Now we observe that there's no door. Right, so here's my new current distribution. And you notice that everything is sort of multiplied as a ratio of 0.1 to 0.9, which is what that observation model tells us, because that's what we did before. Okay, and if we go left, let's go 8, we'll go left. So now we're at position 7, and we'll observe a door. And all of a sudden, all the information we have, we're now at 7. Right, we now have moved from here to here. And now it's pretty sure it's at one of these locations. Right, but it could be at some of the other locations. Right, there's a whole lot of other places it could be. It's very unlikely to be at location 10. It's very unlikely to be here. It's likely to be at one of the other ones. Okay, so let's keep going. Let's go where I'm at 7. Let's go left again, and we'll observe no door. Let's go left and observe no door. And it thinks it's moved left a bit. Let's go left again and observe no door again. Let's go left again and observe no door. And the one that was before was 0, and it's sort of... All right, the previous one, we've gone left and observed no door. So we're going to... So see what happens is that we get this other distribution. If we go left again to 4, we go left and observe a door, all of a sudden it's pretty sure it's at 4. Right? There's a 0.4 chance of getting at 4, even though it's sort of lots of noisy sensors. And we can go left again. So we mess things up. Let's go left again. Let's assume we go left. Let's assume we go left. Let's make an error here. Let's observe a door. Right, you can recover from errors pretty well. Observe a door. And all of a sudden, it's not so sure it is, but it's pretty sure it's around this path there. Right, we can go left again and observe a door, and then all of a sudden, it's pretty sure it's 2. Right, even though it's made errors and noise of things, it's pretty sure it's at 2. And it can wander around, and it finds itself reasonably well, even though it's got noisy systems. So you know how this works. This is just variable elimination with this Markov chain. Okay, I'll put this up so you can play with it, but it's sort of interesting. But you know how it works. You just have the dynamics. You're just going to run through the dynamics and build this up. Okay, any questions about that? Yeah.
When it was at 4, it had a high probability at 4, but not at 7.
When it was at 4, it had a high probability at 4, but not at 7. Yes.
So, but how does it know that it didn't start at 12? How does it know that it didn't start
It doesn't know it didn't start at 12.
But I'm saying, like, why did it know it had a higher probability of 4 than it did at 7?
Because it's unlikely that it's, because it actually went 1, 2, 3 steps and observed something. So it fits well with this hypothesis. But this hypothesis, it would have had to either overshoot or have a noisy sensor. And that's less likely. Right, because there's not an even number of steps in here. And in fact, by doing enough, you could actually, it can find itself reasonably well, even though everything's very noisy. Everything's very noisy. The dynamics are noisy and the other things noisy. It can find itself pretty well just with this probabilistic model. Yes? Oh, has no idea. It's this, because it can't distinguish anything. Right? So if you're driving down a street in suburbia and all the houses look the same, it's going to get very lost. But if it knows where it started, it can count houses and things like that. So it's, right? The Google car does it, probably every 10th of a second it updates. So it sort of knows where it is and it keeps just readjusting. So instead of just driving blindly or just assuming it doesn't know where it is, it's going to it combines both the observations and its model about where it's going. Okay, any other questions? All right. Let's do that. All right. Let's give some other examples. So here's a very simple language model that we saw before. So this is the one that we did before with the help page, right? So this is essentially because we're going to stick all these things together. So we're going to have a help page above this set of word model. So each word variable here is Boolean. It's true when the word's in the sentence and false otherwise. That's the one that you played with before. So the probabilities that are provided, then you know this. You want the probability of A, the probability that the word is A, the probability that the word is aardvark, and the probability the word is Z, appears Z, or whatever it is, appears in your sentence. Okay, so if you condition on how do I phone my phone, then what's going to happen is you're going to observe phone is equal to true, how is true, aardvark is false, etc. Right, so you're going to condition on this and you can work out the probabilities, and if you have a help page on it, you can work out that. All right. So another model, that's a bag of word. This is the set of word model. A set of word model, we're going to condition on this. So here's another model. So we're going to have a sentence. So W1 is the first word in the sentence, W2 is the second word in the sentence, W3 is the third word, and Wn is the nth word in the sentence. And the range of each variable is the set of all words. Right, so the range of W1 is all of the words. And so then the probabilities you're going to provide are the probability of the distribution over words for all distributions. So it's a probability now is the distribution over words. And so if you do, how do you